Good morning, everyone. I'm Floriana Petrone from University of Nevada, Reno. And today, in my talk, I will give you just an overview about a project that was recently supported by Caltrans on the hazard-based risk and cost-benefit assessment of temporary bridges in California. Besides myself, the team working on this project included Dr. Kunat from UC Davis and Mehdi Kashizadeh, a PhD student at UNR. Now, first things first, before really just talking about temporary bridges, let's clarify what we mean by temporary bridges. So when we talk about temporary structure, temporary bridges in this case, we refer to bridge structures that are meant to have a service life of about 5 years. That will be the target, and really just that are constructed during the replacement, repair, or maintenance of ordinary bridges. So for this structure, there is currently no consensus on what is the most appropriate hazard level that should be used for their seismic design. And just to cast this in the appropriate framework, we should consider that current practice for ordinary bridges is based on a hazard level corresponding to 5% probability of exceedance in 50 years, which roughly corresponds to a return period of 975 years. Now, it's obvious that extending this approach to the design of temporary bridges will be overly conservative and not economical. Again, keeping in mind that these bridges are designed to have a service life of 5 years only. And so Caltrans was actually one of the first departments of transportation to identify and tackle this issue. And so back in 2011, they issued a memo to designers advocating the use of spectra, design spectra corresponding to a return period of about 100 years. However, still today, there is no general consensus across all the departments of transportation of what will be the most appropriate hazard level to use for temporary bridges. And even within Caltrans, there's really no evidence, no just rigorous analysis proving that this is still like a good approach to use. And so in this context, really the main objective of this project was to carry out a systematic set of analysis across a range of hazard levels and locations of different seismicity in California to really lay the foundation, provide a strong, rigorous basis for the development of seismic design recommendations informed by risk analysis. All right, just a few words here of what structure, bridge structure we use for our case study and what locations we selected in California. Here you see this nice picture of a typical bridge that Caltrans likes to use for these temporary structures. So we have reinforced concrete crust-in-place columns. Usually Caltrans likes to use circular cross-sections with this lightweight superstructure sitting on the columns and connected through just hinge connections. And just sitting here on the two ends with expansion bearings. Keeping in mind that, again, these bridges have just expected 5 years of life, service life, and so even abutments are not really constructed. It will be too expensive for these structures. And also to have a sense of what we mean when we say that these prefabricated structures are lightweight, we should think about a force applied to the columns, which ranges between 5 and 7% of the capacity, compared to the 10, 12 that usually you observe in regular bridges for Caltrans. Now here on the right, you see a map of California with the 4 just locations we identified for our study. So 2 of them, San Francisco and Los Angeles, are representative of low seismicity sites in California, and then Sacramento and San Luis, high seismicity sites in California, clearly, and then Sacramento and San Luis Obispo of low seismicity sites in California. All right, so, the first thing we did here, after identifying the type of bridge we wanted to work with and the locations, we moved ahead with the bridge design. And for doing this, we just used the basic criteria in the STC 2019, so based on the columns, displacement, ductility. And so for doing this, we need to just calculate a demand and a capacity. For the calculation of the demand, we use the EDA, current dynamic analysis in CSI bridge, and then for the delta Y, so the capacity point, the yielding point, defining the yielding point, we use the model, the linear model developed in OpenSeas. Now, in terms of demand, in terms of spectral acceleration, so here you see the spectra, uniform hazard spectra derived for all 4 locations and for 3 hazard levels. So our just very first approach was to start from what we know, so the 100-year return period, and then go 1 level above and 1 level below. So we're looking here, these 3 spectra correspond to 50, 100, and 200-year return period. These all follow the what Caltrans does for the design. So for Side D classes, also incorporate the current, maybe they will become old shortly, the near field effects from models back from 2014. All right, so, and with reference to the nonlinear model we developed in OpenSeas, what was very important, not only for determining the yielding point, and so the yielding capacity of the columns, of the bridge as a whole, but also because those same models, you will see, will be used a lot to run real-time history analysis. So we ended up putting together a database of about 2,000 just analysis, and so we want to make sure that we could, trust our model. And so here I'm showing an example of how we just carried out the validation of the models with comparison against experimental data. If we're doing this, we use the just data available on the design safe data depot. Really speaking to the importance of having just good and just databases that we can use for a broad just range of analysis. All right, so by this time we really had just everything we needed to complete the design. And here in this table you see a summary of the key data of the design across all the 12 different bridges. And so the locations here, you see some just key information on the geometry. And then if you really want to pay attention to this table and you want to go through this number one by one, you will notice that the reinforcement, both the longitudinal and transverse, for some of these we go below what would be the minimum reinforcement ratio according to the AASHTO provisions for ordinary bridges. However, we just kept the design from the performance-based approach on purpose, without meeting the AASHTO criteria for ordinary bridges. We really want to see what we observe if we really strictly follow a performance-based design, just informed by just the site-specific hazard. And so after having the bridges, so we needed to select a population of records to perform our analysis. And so what we did, we informed the selection of the records at each location based on the hazard aggregation, and we selected 30 pairs of ground motions for each location. In addition to this, we also rotated the ground motion twice to account for any potential orientation of the bridges with respect to the causative fault. And so as a result here this is what we get, for example, for San Francisco in this first row. So this will be the scale spectra, of course, in the bandwidth of interest for these bridges. And just to give you a sense, again, we're talking about lightweight superstructures. And so the fundamental period we expect to see is slightly shifted towards the shorter period. So we are in between 0.85, 0.9 seconds. And here you see how the just median standard deviation of the selected final set looks like for San Francisco as a level 3 and Los Angeles as a level, same as a level 3. When we say as a level 3, we're talking about the highest hazard level, so corresponding to 200-year return period for this, just first part of the study. All right, so, well, at this point we had everything, right? We had all the real-time history analysis, all the responses, and we used the maximum drift as the reference engineering demand parameter, but we really needed some objective criteria to then, classify the response of these bridges. And so for doing this, we used the damage state definition that Caltrans is currently using for ordinary bridges. You see here all these 6 damage states, and you see here a nice description of what will be the visual damage for these just bridges. Very useful for inspection of bridges, not quite for just analysts that work a lot with numerical models. And so at this point, what we had to do, we had to really just translate this description in a phenomenological sense of the damage into objective criteria we could use in our numerical model. And really ended up with this set of criteria based on the stress and strain in the concrete core, concrete cover, and reinforcement to really just fully follow the damage propagation in the columns. Well, at the end of this, we ended up with just a full mapping system where we can just couple the attainment of a damage state with the corresponding drift for just each bridge. So again, you look at all these curves here that represent the bridge design for each location and for each hazard level. All right, so at this point, after running all this set of analysis with the bridges, we started homogenizing these results into statistics. And I'm showing the statistics here in the form, in the shape of box plots, where we look at the just median here, then the 16th and 84th percentile, along with the maximum and minimum values. And you see this across the 4 locations, and then each column represents a different hazard level. Well, not a surprise that we see nice consistency in the results. Of course, this was an hazard-based design, so performance-based design, and so as a result, the performance seems to be consistent with what was our the strongest assumption. And so pretty much all bridges are within damage state 1 and damage state 2, which would be elastic and minor repairable damage. Then based on these just data, we derived the probabilistic demand models, and you see just an example here for San Francisco. And then from this, using the data from our pushover analysis for the capacity and then the median of the other plots for the demand, so we could derive just fragility functions. And so if you look at this summary here of all the fragility functions, each column represents a location and each row represents a hazard level. So you can clearly see that we observe repairable damage across all locations and hazards. And if you want to just have help in getting oriented with this, you should look at this dotted line here, vertical line representing the design spectral acceleration. That really just tells us where we should put just our demand in a realistic way, what we should expect for those bridges and for those locations. Well, but at this point, thinking about that some of these bridges are potentially going to be designed for 100-year or 200-year return periods are going to be in San Francisco, for example, where we know a big event is not expected anytime. So then we ask ourselves, well, what if a beyond design earthquake hits a temporary bridge? So what shall we expect in this case? And so what we did here, we took our bridges, we selected 2 designs, the one corresponding to just 100-year return period, which is indicated here with HL2, and the one corresponding to 200-year, HL3. And we subjected these bridges to the ground motions selected and scaled following this for an earthquake corresponding to 500-year return period, and then 975-year return period, which will correspond to the demand of just a regular, ordinary bridge. Well, not a surprise, as you can see, we start seeing a significant increase in the demand with, just even cases, not, just rare cases where we observe collapse of the structure, especially in the locations of higher seismicity, but also if you see here in the second row, when we look at San Luis Obispo or Sacramento, we start seeing just significant damage in the structures. Well, then we use this data once again to produce, the statistics and to look at the just fragilities. And so here we started comparing, one by one, the demand here and the expected damage at the corresponding spectral acceleration for that return period. And once again, you can see when you compare the 2 designs, how we just observe a higher probability of exceeding, for example, damage state 4, which would be the first, say, concerning damage state. We talk about, concrete core crashing as we move from hazard level 2 design to hazard level 3 design. Well, at this point, so having all this data available, so what we did, we carried out full just risk analysis. And so what we did for doing this, we used the total risk just model, and we used 3 different lifespans. And it's interesting because this was one of the most popular questions we got when we presented. We shared this work with you last time. We say that temporary bridges are going to be there for 5 years, but are we sure that after 5 years, we're going to demolish the structures? And this was a very, raised a lot of questions and nice, discussions. So as a follow-up on that, we thought it was really good feedback. So we calculated this risk for 3 potential lifespans. Well, 5 years, which is our target for Caltrans to replace or repair, the main bridge, and then 10 years and 15 years. So for doing this, we calculated the probabilities of exceeding each damage state at the design spectral acceleration. And so in other words, what we did, we used the probability calculated with all the return periods, for example, 200 you have seen, 500, 975, and then we used this data point to interpolate and obtain a new fragility function, which is, as an example, is the same fragility function we see here. And then we combine this with the hazard at that specific site, and as a result, what we obtain are these tables that are really just that we provide to Caltrans to make a risk-informed decision on what would be the most appropriate just hazard level to use for the design. And so as an example, just there are different ways we can use this data. I'm showing here just a portion of all this data we are providing to Caltrans. And for example, for damage state 3, which would correspond to moderate damage. So it would be really on the Department of Transportation to really choose what risk, just to take, and what in terms of exceeding, and I think this damage state, a moderate damage, if, for example, we consider a hazard level 2 design or a hazard level 3 design. And if we compare, for example, the case of 15-year lifespan, so we go from 4.14 to 3.75. Well, this change can be, just deemed as a minor change. So just sticking to, just the current design approach for temporary bridges, or can inform just the update of current, the current provisions for temporary bridges to go to hazard level 3, so 200-year based design. Now, based on all these, just results we have collected so far, and really we just only scratched the surface, with this work here, just on this topic. We believe that hazard consistent design for temporary bridges across locations of different seismicity performs satisfactorily even for lifespans that exceed the expected 5 years, and when the AASHTO minimum requirements for the design of ordinary bridges are not satisfied. So it means that Caltrans can think about, just going below that. We know that 1%, just threshold for longitudinal reinforcement. And, just to add one more, just a piece here, this is also supported by the fact that the minimum design requirements are related to containing the creep phenomena in the concrete. But when we have lightweight superstructure, we also know that we have just less severe creep phenomena. And so this really can support also the idea of using, just less reinforcement in temporary bridges. Finally, here also it is demonstrated that designs corresponding to a return period of 100 or 200 years have similar risk of moderate damage, suggesting that the current, just approach that Caltrans is using that was based on good engineering judgment is actually satisfactory. So if, that would be the choice of Caltrans to keep using it 100 years, we demonstrated that there is a basis. I mean, there is, there are good reasons for that. However, and we would really like to have Caltrans support for doing this, we think that there is a lot more to do. So something we would like to look into is what if we use, instead of using those lightweight superstructures, we use full weight superstructures. So girders, prefabricated, precast, just girders. Second, we think we need to develop new damage states, simpler for these bridges, potentially just based on the three, just sort of like the way we tag buildings. And so like a green, yellow, and just red classification for damage states. And then third, just very important, we want to look at the impact of multi-span configurations and substructural irregularities. And I'm providing here an example of this bridge. Is a real bridge on the Dr. Fine Bridge on the US 101 over the Smith River. And as we speak, this bridge is there as a temporary bridge that is there because of the reconstruction of the original just bridge. And clearly is a configuration, more, complex and articulated compared to what, just we have used in this very first, analysis. And with this, we'll conclude here. And in case you have an interest in looking more into what we, have briefly discussed today, there are, just a few references here. The Caltrans report, of course, and then, just papers, conference, and potentially also a journal paper. And I'll stop here and be happy to take questions.